Okay, so first, who am I? I'm Raphael. I worked at Ledger as a senior backend staff engineer, and I'm working mainly on indexing blockchains using Scala and PostgreSQL. That's all my contact if you want. So what's Ledger? Ledger is a company selling some hardware to protect digital assets like identity, crypto money, and so on. It's basically we're in 9 locations, more than 600. It's a really techy company, and all our backends are Scala with some quite good numbers handling per service, something like 30K requests per second. And if you want, you can come join us. So let me tell you a story. Suppose you encounter in your code base a case class for IBAN, so it's international bank account number. Here it's a French IBAN, so you have 6 fields. And yeah, it's instantiated simply until you find this. So you even try this and it works. It compiles. It will fail at the moment, but it compiles. We can do better. How? So first, maybe type aliases. It will say that say to the developer that which string is a country code or a bank code and so on. Yeah, sorry. But that's only type class. We can always basically there are not type aliases. Sorry. We can always mix up the fields because they're basically strings. So let's try with value classes. We have to define all 6 value classes. And now it's a little bit more verbose, but it works well. This doesn't compile anymore, but this still compiles and will still fail at runtime. So, okay, let's add validation. So for each case class, we have to require and says, okay, this contains 2 characters or 5 or 11. And as we are using require, it will crash at runtime with assertion error, and we don't want to crash if someone gives you bad data. So first we define our error, and then for all 6 classes, we have to define the parse method that validates the data is good. So the parse method, and for each, we return an either if the data is bad or the good type if it's good. And we have to do this for all classes. And we're using Scala 3. So what about opaque types? Because basically it's just strings, and we want to put some meanings on this string. So that's really the use case for opaque types. So let's define one. So branch code will be a string, and we're at no cost wrapping a string into a branch code. and getting the value as an extension. And then again, the parse method that, that validates the data. And this has to be done for all your domain model. So just a quick recap before going on. Here, I don't know if you see well, there's the legend. In the first column, we have the legibility. So we see that row classes fail at all requirements. So we have legibility, strict order, validation, referential transparencies, performance, and conciseness. So when we add type alias, we only add legibility. Value classes add strict order and validation, simple validation with require doesn't allow referential transparency, but either does, and opaque types is more performant than all these thanks to the lack of overhead. But we could be better again. So let me introduce you Iron. What is it? It's a composable type constraint library, which enables to bind constraints to directly into a specific type. This was created in Scala 3 2 years ago by Raphael Lemaitre, and I'll dive into it. So first, Iron is a constraint library. So what is a constraint? Basically, it's just a tag, a final class with no other implementation, no data, no operations. And then, on top of it, we define an implicit constraint that says, OK, positive applies to int, and we define two methods, test that do the check, and message, which will be the message in case of error. You see that both methods are inlines that will allow to do this check at compile time. So here, that's how we use Iron. So we just say, OK, it's an int, and we apply this constraint. So this compiles perfectly, and this will fail at compile time, saying, oh, it should be strictly positive. We can compose constraints. So there we say, OK, positive, strictly positive, but less than 42. And again, if we give another value, it will be a compile time error. And each time the message will say which constraint of the two failed. So, validation, how it works. Here, we see simple code, but there's a problem with this code, because it doesn't compile and say, OK, I can't apply the constraint at compile time, so either you use the refine methods or inline this value. So we have two ways. The first, we just define inline, and the compiler inlines it, and then it can apply the constraint, check the constraints, or it will be done at runtime. So for the second, it's cool, but here we are using running unsafe, and with an invalid value, we'll have an illegal argument exception with the message. So there's let's go back to our example of IBAN. Then we can create IBAN using strings and say, okay, the first, it should be alphanumeric and 2 characters, and so on, and then you can construct your IBAN easily. And also, we're in Scala 3, so we can use, and we want to use opaque types and embed the constraint directly into the opaque type. So here, we're saying that we want that positive will be an int, but greater than 0. And to allow using and constructing easily this positive, we have to define an object that extends these traits, refine type ops, saying the first argument is the base type, then the constraint, and finally the domain type, let's say. So that's an example directly taken from our code base. Here we wanted to have a class representing satoshis, which are the smallest amount of bitcoins. So we know that a satoshi is always positive or null, and we also know that there will be only 21 million bitcoins in possible. So and one satoshi is 100 million satoshis are doing a bitcoin. So here we have fully using these 3 lines define our satoshi, and it's validated everywhere we use it. So in summary, I took the same chart, but adding another column, which is the compile time checking, because all the other methods were only done at runtime, and we want to do it as soon as possible because a bug that is detected, the sooner a bug is detected, the quicker it will be fixed, and we don't want to be awakened at night because some bad data arrived. So here it's checked only at compile time. Another reason we used Iron, it's Iron loves Scala ecosystem because it can be used with not only standard lib outputs, such as either options, but if you're using type level, you can use validated or either plus parallel or Zio validation. And there's a lot of integrations. For Tapir, you have the validation in your endpoint. It supports 5 maybe 6 now, JSON library, JSON and a bit more because Borer also supports CBOR. For databases, there's integration on Doobie and Skunk. It's possible if you want to use other to write integration, I will show you after. And for other stuff like config with Cyrus, test with Scala checks, and all the arbitraries are generated for your constraint types, and see a decline for the CLI. So here again, it's we'll take a case class from our code base, which is a tag, which has a name and a value. We want the name to be non-empty and have at most 128 characters, and the value non-empty and at most 512. So we define our constraint types, and then we use it in Tapir. Here, our query is the tag. And so as the tag is two fields, it will automatically be read and validated by Tapir. But at the other end, we store it in a database. So here we take the tag name and the tag value, and directly, that's the meta for Doobie, that serialize the values for the database. So how can we say that you can write your own integration if it doesn't exist yet? And brace yourself, I will show you the entire Doobie integration. That's it. It's two givens. The first, how can we have a meta from a constraint type, knowing that there's a meta for the base type and a constraint, and the other is for opaque types, and then we use a custom mirror in Iron that allows us to have the correct type. Here we have the Iron type, which is the correct type. And that's all. So, oh, I was quick. First, Iron allows us one big thing is that we can't have an illegal state. So that's the famous Jan Minsky quote. Something else, it's reduced the feedback loop to a minimum, because before using this constraint type, it occurred that even in production at night we have some weird errors, and so we added test, integration test, unit test, and the quicker is always the compilation time. It's, as I said, noticeably increased the reliability and legibility of our code. And yeah, Scala 3 type system is a blast, and use it at maximum. Thank you. Here you can find on the left side slides, and if you want, there's a feedback form for me, so I can get better the next time I'll be in front of you. Thank you.